So good afternoon to all. It is my pleasure to introduce Dr. Eli Adashi, a highly distinguished academic physician, scientist, and national leader in reproductive medicine and health policy. For those of you who are not familiar with him, although I'm sure the majority of us are, Dr. Adashi is the former 5th Dean of Medicine and Biological Sciences at Brown University, currently serves as a tenured professor of medical science at the Warren Albert Medical School at Brown University. He received his medical degree in 1973 as a member of the inaugural graduating class of the Tel Aviv University School of Medicine, and he later earned a Master of Science in Healthcare Management from the Harvard T.H. Chan School of Public Health. Dr. Adashi completed residency training in OBGYN at Tufts University and went on to pursue fellowship training in reproductive endocrinology and postdoc training in reproductive biology at Johns Hopkins University and also the University of California, San Diego. And over the course of his career, he's held faculty appointments at the University of Maryland, University of Utah, and Brown University. He has served as chair of the Department of OBGYN at the University of Utah Health Sciences Center, where he founded and led the ovarian cancer program at the Huntsman Cancer Research Institute. And at Brown, he served as Dean of Medicine and Biological Sciences and as the Frank L. Day Professor of Biology from 2004 to 2008. He's widely recognized for his leadership in academic medicine and professional societies. He's served as president of the Society for Reproductive Endocrinologists, Society for Gynecologic Investigation, and the American Gynecological and Obstetrical Society. And he's also held senior leadership roles within the American Board of OBGYN. In 1999, Dr. Adashi was elected to the National Academy of Medicine, and he served on numerous National Academy consensus committees addressing issues near and dear to all of us, such as premature birth, women's health research, stem cell research, maternal mortality, including co-chairing international efforts to reduce childbirth mortality in Indonesia. He's a prolific scholar, a dedicated mentor who's trained more than 50 postdoc fellows. He's the author or co-author of nearly 900 peer-reviewed publications and book chapters. He's edited or co-edited 16 books and served in major editorial leadership roles for many scientific journals. His work's been featured in prominent media outlets, including New York Times and Washington Post. And beyond academia, Dr. Adashi has advised the U.S. Department of State, the CDC, the World Health Organization, the World Bank, and several major foundations on issues related to women's health and reproductive medicine. So he continues at Brown to teach and mentor medical students. He directs courses on healthcare policy and the U.S. healthcare system. So as you can see, this is a very tremendous role model and busy man, and we are so honored to have you speak with us today, Dr. Adashi. We appreciate your acceptance of our invitation, and we look forward to hearing your updates. Thank you so much.
Thank you, Trina. This was rather exceptional. Uh, Maybe I can thank you in person on a separate occasion, uh, even if it's by phone. In any event, we're going to be speaking today about the future. And really, the subject matter, even though I think I may have addressed it to some degree, even at your school, it has moved forward in a significant way. And this is quite exciting, quite novel, and really offers us all an eye to the future. But before we go there, I think we will all do well to remember that in 2 years from now, we will be celebrating the 50th anniversary of IVF, which was started, of course, in the UK in 1978 by Dr. Steptoe and Dr. Edwards, this being their Lancet report in 1978 of this remarkable achievement, as a result of which we witnessed the birth of Louise Joy Brown, who is shown here in the arms of her mother, Leslie. Professor Edwards received the Nobel Prize in 2010 for this accomplishment. You might ask why his collaborators, Dr. Patrick Steptoe and Jean Purdy, did not receive the Nobel Prize. And sadly, this has to do with the fact that both of them passed away before the 2010 event. And it is a policy of the Nobel Prize Committee to award the Nobel Prize only to living recipients. And so only Dr. Edwards was available at the time to receive the award. Dr. Edwards himself passed away in 2013. This is a Lancet obituary that was published at the time. In the US, you may recall that it took the Norfolk team to see to the birth of the first US IVF baby, who was born on December the 28th, 1981. Shown here are Howard and Georgiana Jones embracing the baby in question. The baby in question was known as Elizabeth Jordan Carr. She was the first American IVF baby, shown here in the arms of her mother on the pages of the Boston Globe, and in this case shown on the front page of Life magazine. This was clearly a huge event, and it graced the front pages of many leading journals. But going forward, we are now switching to a modification of IVF, perhaps a simplification of IVF, courtesy of in vitro gametogenesis. But before we do that, we might do well to look back at the futuristic efforts of Aldous Huxley, who in 1932 published Brave New World. And in that particular book, he made the following predictions: that eggs will be created via ex vivo ovarian cultures, that embryos will be born via in vitro fertilization, and that newborns will come about via ex vivo ectogenesis, that is to say, an artificial uterus. Of all of these predictions, we know full well that the prediction of IVF was right on. The other predictions did not materialize as yet. In chapter 1 of Brave New World, the director of hatcheries and conditioning says, one egg, one embryo, one adult, normality, making 96 human beings grow where only one grew before, progress. And the fact is that in vitro gametogenesis, we deal with 96 well plates all the time. And in theory, of course, this could lead to 96 human beings. Now, the beginning, as is always the case, was modest, and I have to say is entirely attributable to the efforts of two leading Japanese investigators. Mitinori Saito, MD, PhD, is from Kyoto University, and at the time that IVG was developed, he worked very closely with Katsuhiko Hayashi, PhD, who effectively served as a postdoc with him. Later on, Professor Hayashi moved on to Kyushu University to establish himself as an independent investigator. But when IVG was born, the two of them were critical. Now, to even utter the term, we need to appreciate the concept of stem cells, which come in two varieties, embryonic or induced. And I'll go into that. But stem cells have the potential capacity to create any cell type in the body. Motor neurons, for example, maybe amacrine neurons in the retina, and for that matter, dopaminergic neurons in the striatum. Examples of this abound. For example, Nature reported on a gentleman who was paralyzed, but upon injection of stem cells into his spinal column, he was able to resume some degree of mobility. Similarly, the injection of stem cells to the substantia nigra gave rise to some improvement in Parkinson's disease. And so there clearly is a therapeutic potential here that we must not lose sight of. But of course, today's presentation is focused on stem cell-derived gametes. Science magazine did not lose sight of this major breakthrough and published a full spread in 2021, authored by the two originators, Mitsunori Saito and Katsuhiko Hayashi. The New England Journal of Medicine, not to be outdone, commissioned a similar paper from Mary Herbert and Azim Surani from the UK. The paper was titled Oocytes from Stem Cells. In 2023, I had the privilege of organizing a 2.5-day workshop under the auspices of the National Academy of Medicine. And at that time, numerous investigators from the United States and abroad discussed the latest information on in vitro-derived human gametes. Mind you, the Nuffield Council on Bioethics, which is a British enterprise, clearly did not lose sight of in vitro-derived gametes either. In fact, you can see that they have placed in vitro-derived gametes at the top of their agenda. Yes, they were going to deal with this subject, this subject, this subject, this subject, this subject, and this subject, but in vitro gametogenesis topped their agenda list. We can probably all agree that in vitro gametogenesis is a disruptive technology. Whether or not it's achievable in a human is something we need to discuss. It's not completely clear at this time. And what the timeline is even less clear at this point in time. But as I said, at the basis of all of this are stem cells, and we have to say something about how those are created. The first type of stem cells are created by somatic cell nuclear transfer. This is no longer widely used, but historically it's important to note that this type of stem cell was created in 1958 by John Garden, who was then at Cambridge University. John Garden very sadly passed away only a month or two ago. The way he approached the problem is by transfecting an enucleated oocyte with a somatic nucleus, creating effectively a quasi-zygote and extracting from that structure embryonic stem cells. However, in 2006, a simpler method evolved, so-called induction technology, by Shinya Yamanaka from Kyoto University, who published his paper in Cell. Simply put, he started with somatic cells, transfected them with select transcription factors, and gave rise to what we call induced pluripotent stem cells, which is really the kind of stem cells we mostly make use of today. Nevertheless, both individuals received the Nobel Prize in Physiology and Medicine in 2012. Now, in vitro gametogenesis requires, of course, that we start with a somatic cell, that we convert it either to an embryonic or induced pluripotent stem cell, and then guide that pluripotent stem cell towards a gametogenic fate. Now, that's easier said than done. What are the prerequisites? Well, you have to know the cues which would lead to the desired outcome. You need to know the sequence by which they are applied. You need to know the timing by which they are applied. And you need to take into account the niche in which the target is encased. I don't have to tell this audience that oocytes are surrounded by granulocyte theca cells, and that sperm are surrounded by Sertoli cells. And that's the niche. And you have to take that into account whenever you think of making any meaningful changes in the germ cell element. The beginning was modest and dates back to a science paper in 2003, the leading author of which was Hans Scholler, then a postdoc at the University of Pennsylvania, but eventually today, director of the Max Planck Institute for Molecular Biomedicine in Germany. But in that science paper, an early version of an embryonic stem cell that led to an oocyte is shown on the right lower hand side of the slide. That same year, Toshiaki Noche from Japan reported the same finding on the pages of the Proceedings of the National Academy of Sciences. In 2004, George Daly, now the dean of Harvard Medical School, reported on the pages of Nature the derivation of embryonic germ cells and male gametes from embryonic stem cells. And René Rehopera, who at the time was at UCSF, reported some of the same. In the years that followed, several papers saw press in Nature, in Science, and in Cell, recapitulating and refining the experience. The same that was in the rodent, I should say, and the same held true for the human. And so when we look back at where we stood in 2015, we can say that the germ cell specification pathway clearly was not conserved between the rodent and the human, and that the genetic networks involved were also quite distinct as well. So what we knew essentially in 2015 is how to convert stem cells to primordial germ cell-like cells. What we didn't know in 2015 is how to convert the latter to haploid postbiotic mature gametes. In a word, We mastered the extragonadal component, but we had yet to master the intragonadal component thereof. The final frontier was, of course, in vitro gametogenesis all the way. The first person to accomplish this was our friend Katsuhiko Hayashi, who published in Nature in 2016 on the reconstitution in vitro of the entire cycle of the mouse female germline. He started with stem cells, combined them with gonadal somatic cells, created primary oocytes, eventually M2 oocytes, fertilized egg, a blastocyst, and pups. In a word, he took the process all the way from beginning to end. More of the same was accomplished in a male by his colleague Pitinori Saito. But the human paradigm has not fared as well, and we're nowhere near accomplishing what we would like to. The only published effort in this area is from 2018, the lead author being Mitinori Saito, who started with primordial germ cell-like cells, combined them with genome-generic ovarian cells, and could take the process all the way to the orgonial stage. But he could never produce an M2 oocytes, which is to say, we're still falling short of our ultimate goal. This aside, we can already see the scientific and translational promise of in vitro gametogenesis. For one, it will provide an inexhaustible supply of germ cells, which investigators have all kinds of ideas for. It would allow for functional null mutant analysis. It will allow to study germ's somatic cell interactions. And on the clinical end of things, it could reverse germ cell failure by autologous gamete replacement, gene-edited gamete replacement, and even could lead to same-sex parenthood, which is a separate lecture and a separate conversation. But the point I'm trying to make here is that in vitro gametogenesis has practical applications. We're not there yet, but the potential to accomplish these very important elements is clearly there. And in my view, it's just a matter of time. IVG will also impact on IVF because it will eliminate the need in stimulation and egg retrieval, in principle. It will do away with gamete donation, which currently we rely on in the form of donor banks. It will convert IVF effectively to a laboratory procedure. It will still require endometrial preparation and transfer because an embryo will have to be replaced in the endometrial cavity. And in principle and in theory, this approach could improve affordability and thus access when compared with conventional IVF. I say this with some skepticism only because I have observed the American genius to jack up prices under all kinds of circumstances. And even though this process should in principle be more affordable than IVF, it's not clear that in reality it will end up in this capacity. Professor Vitalipov from Oregon published in Nature very recently a paper on the induction of experimental cell division to generate cells with reduced chromosome ploidy, clearly an entree to in vitro gametogenesis, and others have taken various steps to get to that point. The NAFED Council, which is an ethics organization, analyzed the ethical and policy questions related to IVG. And for those of you interested, I strongly recommend this compendium to read. In the US, of course, if IVG were to come to pass, it would have to be subject to federal regulation, specifically by the FDA. And in the FDA, there exists an entity called CBER, Center for Biologics Evaluation and Research, which will almost certainly be the body in charge of evaluating IVG and clearing it for clinical use if, in fact, they come to that conclusion. I should say that as we speak, there are very, very early commercial US efforts to capitalize on IVG. A company called Gamito, which is based in New York, is trying to develop a product called Fertillo, which ultimately, according to their material, will simplify and shorten IVF, and I'll show a slide of that. Uh, at this point, they did receive FDA approval for phase 3 clinical trials, which is to say that the process is proceeding towards application. As viewed by Fertillo, the product that they have in mind will reduce the duration of IVF stimulation from 12 days to 3 days, which will obviously be a significant relief to the women who currently have to undergo 12 days of stimulation to undergo IVF. Fertillo cycle requires 2-3 days of in vivo gonadotropin stimulation, thereby reducing the gonadotropin requirements by circa 80%. In principle, that too should reduce the price. Fertillo's ovarian support cells see to the in vitro maturation of retrieved immature eggs, which again is remarkable. And as I mentioned, Fertillo is now in phase 3 clinical trials. This brings us to a point where we have to say, stay tuned, because much more needs to happen before IVG becomes a clinically usable entity. But we can say that we are well on our way with a technology that we could not have foreseen as recently as a few years ago. And so I'm glad I was in a position to share with you what is possibly down the road for all of us to see and take advantage of. So thank you very much for your time and for your attention. It's been a pleasure. I'll do my best to answer any questions, should there be any.
Thank you, Dr. Adachi. Such interesting history, and I love the perspective. Um, I wonder if you can comment on maybe lessons learned from development of IVF that were taken into, or maybe perhaps with that knowledge we were able to accelerate, or if you think it will kind of accelerate development and advancement of IVG.
Well, IVF is really the underpinning of IVG, and those two together really will serve women well. Um, but IVG really makes a huge difference if successfully applied, uh, both in terms of the duration of the effort, the efficacy of the effort, and in theory, the costs of the effort. So IVF and IVG are really, are really joined at the hip to improve reproductive functionality uh, as we know it today. Well, I'm going to assume that clarity won the day, and that therefore we don't have to dwell too much on questions and answers. And if that's agreeable to you, Trina, maybe we can call it a day.
Yes, of course. That sounds great. Thank
All
you
right,
so much for being with us.
my distinct pleasure.
All right, take care.
Bye bye.
Bye bye.